Let us start from the seventh problem. The statement of the seventh problem is in the double slit experiment, the angular width of the fringe is found to be 0.2 degree. On the screen, placed 1 meter away. The wavelength of the light uses 600 nanometer. What will be the angular width of the fringe if the entire experimental apparatus is immersed in water? So this apparatus is immersed in water. Now what you can do is mu is equal to lambda air divided by lambda medium. Lambda medium is lambda air divided by mu. Lambda medium, lambda air. Now lambda air, just remember this line. Now angular width theta is given by lambda by d. Angular width, the formula for angular width is lambda by d. Let me write this formula directly here. So we will conclude the problem here. Now angular width theta is given to be equal to lambda by d. So this was in air. And now we want to know its value in this lambda medium. Now if I take this ratio, so I will put this as equation number 1, this as equation number 2, and this is equation number 3. And now theta dash, and this is medium. Theta dash is lambda medium divided by d. I will put the value of lambda medium. This is lambda divided by mu, and this is d. This is lambda air, and this is again lambda air. Lambda air divided by this d is mu. So theta dash is equal to lambda a divided by this d. Lambda a divided by this d. This is theta. So this is just theta by mu. So if you have to find out the new angular width, just divide the old angular width by refractive index. Again, one more shortcut. Just divide the old angular width with refractive index. You will get the newer one. Here old value was 0.2 minutes. Minute or degrees, let me check it. It was 0.2 degrees. So 0.2 degrees divided by 4 by 3. This is just 3 by 4 of 0.2. It will come out to be 0.15 degree. So here is a shortcut for this. Kindly note this shortcut. Now next, let us come to the next problem. What is the Brewster angle for air to glass transition? He has given us air to glass transition. This is a simple problem on Brewster's law, and that is tangent of polarizing angle is refractive index of glass with respect to air. So this is the formula that we use. Polarizing angle is the angle at which reflected light becomes plane polarized. So this is this, and tangent IP. So mu is given to be 1.5. So we want to find IP. So Mu is given to us. We want to find IP. Now IP is tan inverse mu glass with respect to air. IP is tan inverse 1.5. 1 corresponds to 45 degree when we take tan inverse, and 1.5 corresponds to, no, it's quite clear, this corresponds to 56.3 degrees. And now the next question. Light of wavelength 5000 angstroms fall on a plane reflecting surface. What are the wavelength and frequency of the reflected light? It will be same. For what angle of incidence is reflected light normal to the incident light? This is important. The frequency you can easily calculate. I will change the color here. For the calculation of frequency, he has given us wavelength lambda 5000 angstroms. C is 3 into 10 raised to power 8. So C is equal to frequency into lambda. If we want to find out frequency, this is this by this. So frequency is 3 into 10 raised to power 8 divided by, we have got lambda. Lambda is 5000 angstrom and this is 500 nano. 10 raised to power minus 9 nanometers, and from here we can easily find the value of frequency. This is found to be 6 into 10 raised to power 14 hertz. And now what is given? What is important is, what is the wavelength and frequency of the wavelength is same and frequency we have calculated. For what angle of incidence is the reflected ray normal to the incident ray? Reflected ray I, this is equal to 90 degree. When the reflected ray is normal to the incident ray, I plus R is equal to this. And now from laws of reflection, we know that angle of incidence is angle of reflection. It means 2I is equal to 90 degree. It means I is equal to 45 degree. So this means that for angle of incidence 45 degree, the reflected ray is normal to the incident ray. Now, 10th NCERT. Estimate the distance for which ray optics is a good approximation for aperture of 4 mm. Wavelength is given. It means Fresnel distance. Aperture is given. Aperture means that A is given. And this is the Fresnel distance which we require to follow. Ray optics is valid up to Fresnel distance. Remember this key. Remember this hint, or you can say the basic point in this case is ray optics valid up to Fresnel distance. And now let us see the formula for DF. Fresnel distance is aperture width square divided by lambda. And now aperture has been given to be 4 mm, 4 into 10 raised to power minus 3 whole square divided by lambda. This is 400 nanometers, 10 raised to power minus this. And from here you can make calculations and you can find out this 4 into 10 raised to power minus 6 divided by 4 into 10 raised to power minus this is 40 meters. And after this, the bottom line for the last problem was that ray optics is valid up to Fresnel distance df, and that Fresnel distance is given by a square by lambda. And now the 11th problem that I shall be taking, this is the problem of a star receding away based on Doppler effect for light. Remember, Doppler effect for light is symmetric and Doppler effect for sound is asymmetric, and also Doppler effect for sound is longitudinal and Doppler effect for light is longitudinal as well as transverse. Now let us note down. Now delta lambda, a redshift is given. Redshift when the star recedes away and blue shift when the stars are coming closer. So the formula that I shall be using for redshift, we take negative sign, and this is very important. And from here we calculate the value of V. Value of V will come out to be C into delta lambda, C into delta lambda divided by lambda. Now C is given 3 into 10 raised to power 8. Delta lambda is given, I think, 15 angstroms, and lambda is given 65, 63. From here we can make calculations and we can get the value of V to be 6.86 into 10 raised to power 5 meter per second. Now the next problem, explain how corpuscular theory predicts that the speed of light in a medium, say water, is greater than speed of light in vacuum. Is the prediction confirmed by experimental determination of speed of light in water? If not, what is the alternative picture of light consistent with experiment? This I think is not an important concept from competition point of view, so I will leave this and I will directly shift to the next problem. Huygens principle leads to law of reflection and refraction. Use the same principle deduced directly that a point object placed in front of a plane mirror produces virtual image whose distance from the mirror is equal to the distance of the object from the mirror. Now this can be asked in MCQs like this. Can you prove this thing by Huygens principle? Always remember, Huygens principle proves laws of reflection and refraction. It means all the predictions or all the calculations made on the basis of laws of reflection and refraction, they are also driven out of the Huygens theory. Now, this is an important concept that I may be taking just 1 or 2 questions from here. Speed of light, nature of source. No. Speed of light, basically, nature of source, direction of propagation, motion of source or observer, wavelength, intensity of wavelength. On which of these factors, if any, does depend speed of light in vacuum? Speed of light in vacuum is independent of all the factors listed above. What is nature of source, direction of propagation, motion of source or observer, wavelength, intensity of light? No. Speed of light is independent of all of these. And next is the speed of light in medium. The speed of light in medium depends upon the speed of light in medium does not depend upon the nature of the source. The speed of light in medium is independent of direction of propagation as the medium is isotropic. The speed of light has got two formulas, always remember. For mechanical wave, this is elasticity by density. For electromagnetic nature, this is refractive index and electrical permittivity. On this, speed of light depends. So now let us see. The speed of light is independent of motion of source relative to medium. The speed of light in a medium depends upon wavelength. It is directly proportional to wavelength. We know refractive index mu. We are familiar with mu is equal to C by V. This is lambda air divided by lambda medium. So this is refractive index of medium with respect to a. The speed of light in a medium is independent of intensity. The speed of light in a medium depends upon refractive index. And now, with these words, I finish this session of NCERT, and we will do the next session very soon. Until then, I pose one problem to you. For sound waves, the Doppler formula for frequency shift slightly between the two situations. Source at rest, observer moving. Source moving, observer at rest. The exact Doppler formula for the case of light waves in vacuum are, however, strictly identical. Explain why this should be so. Would you expect the formulas to be strictly identical for two situations in case of light traveling in a medium? For sound waves, first he takes the case of sound waves. Doppler formula for frequency differs slightly between these two cases. The Doppler formula for light wave in vacuum is identical. As I have already stated you that Doppler effect in light is symmetrical and in sound it is asymmetrical. Would you expect the formula to be strictly identical for two situations in case of light traveling in a medium? So you have to post the answer of this question, and before finishing this lecture I will request all of you to kindly share these videos and comment on it. And even if you don't do this thing, then kindly post the answer of this question in the comments. With these words I finish today's lecture.